Welcome to section 6.1. Let's do the notes on day 1 where we're looking at area between the curves. So when you look at this, what we're after is maybe just shade in the regions we're interested in. I want to find out the area between the blue curve and the pink curve. And how would you go about doing that? Well, you would take, and one way you could do it is to calculate the area under the blue curve. Get the total area from the blue curve to the x-axis. That's what we've kind of been working on up to this point. And then I could also go find the region under the pink curve. And if I were to subtract that purple region from the blue region, it should leave me, if I take this away from that, it should leave me that red region. So we're going to condense it into one formula, and that formula will look like area is equal to the integral. I had markings from A to B, so I'm going to use those as my bounds. And I want my top curve, which we were calling f of x here, so maybe even write in f of x curve, minus the bottom curve, g of x, that's that purple region that we were taking away, and multiply that length by the width dx. So this is actually a width of the rectangle, and this turns out to be the height of the rectangle. So I end up with this idea here where I have a rectangle like a Riemann sum. I've got width dx, and I've got the height from curve f minus the height from g, and leaving me that red region. So there's the formula, and let's just go through and do a couple examples. When I look at example 1 here, I see there's a quadratic as well as a linear function. Pretty obvious how we can make those assignments. So y equals x squared plus 2 on that one. And then I get 2 more equations. Those are vertical lines. So I have a vertical line at x equals 0. And I have a vertical line, I'm just going to draw it about there, at x equals 1. So I really get 4 equations defining the space between the 2 curves and the vertical lines that act as boundaries for us on this problem. All right, so it says decide the upper and lower function. We did that. We have upper function and the lower function, and then set up the integral as well as the intervals. So what I need to do is let's find out our intervals. We're going to integrate between 0 and 1 for our x values. Our top function is x squared plus 2 minus the bottom function, which is a negative x, multiplied by the width dx. So if you want, you can think of this as top curve minus bottom curve. Now it says go ahead and solve this work. Okay, that will be fun. Been a while since we've solved functions by hand. I am going to organize that in descending order, correcting that negative, making it a positive. And let's go ahead and integrate. So we'd have 1/3 x to the third plus 1/2 x squared plus 2x, evaluating from 0 to 1. So 1 goes in first. We'd have 1/3 plus 1/2 plus a 2 minus, don't automatically assume that everything's going to zero out. Play through it. I'd have a 0 plus a 0 plus a 0. In this case, yes, putting the 0 function or the 0 value into the function made it go to 0. Now I think I'm going to go to 6th and make like denominators. So I'd have 2/6 plus 3/6 plus 12/6 for a grand total of 17/6. And of course, it would be units squared since we're talking area. So there's example 1. Not that difficult to do these. especially the ones we're focusing on today. Okay, example 2, I see once again we have a quadratic facing downward and the line g of x equals x. So let's just identify our functions. There's g of x equaling x, and then I have function f of x equaling 2 minus x squared. The region we're going to be calculating for area, let's shade that in, so make sure that you understand what we're after. We're going to get this region between the two curves. And since I clearly have a top function, let me just walk over. I want to trace over. There's my lower function. And then the upper function is green. And it always is above the blue, no matter where I'm moving along horizontally. I'm just going to take a vertical line here and show you what I mean. So in a vertical alignment, the green function always has a higher y value than the blue function. And that's always important to check, because if it is not always, then I might have to break this up into two different regions, which is what we're going to look at tomorrow. So decide your upper function, decide your lower function. I think we've already picked that out. F of x equals my upper function, and g of x is the lower function. Find the points of intersection. Oh, they did not give us the vertical bounds this time. So we need to go ahead and find that. How do I find out what they have in common? Well, it's where they're equal. So let's take 2 minus x squared, set it equal to x. Solving a quadratic, I know one technique is to use factoring. So I'm going to do that. And is that factorable? It does indeed look factorable. So an x plus 2 and an x minus 1. That means I have two solutions. Get a negative on that. So I got x equals negative 2. That looks like this value right there, doesn't it? And then I have that other one at intersecting over there at 1. Now that I know what I want to integrate between, think of that vertical, those rectangles dropping in here. They would have a width of dx, and the length of my rectangle, or the height of the rectangle, is f minus g. So I'm going to go ahead and set up my integral as an integral between negative 2 and 1, top function, which is f of x, minus my bottom function, g of x, dx. Now, if the AP identifies them as f and g, you can as well. I think this one, yeah, let's go ahead and solve it by hand. What was f? 2 minus x squared minus x for g of x dx. And then I'm going to integrate it. I kind of like things organized, so I'm going to put them in descending degree order, and now integrate. So I'd have negative 1/3 x cubed minus 1/2 x squared plus 2, evaluated from negative 2 up to 1. So now we've got to plug in 1. That's pretty easy, isn't it? It'll give us negative 1/3 minus 1/2 plus 2. Take away, throw in negative 2. I would have minus negative 8. So 8 over 3. Negative 2 squared would be 4. 4 divided by 2 is 2 with the minus sign. So minus 2. And then negative 2, oops, just positive 2 there, no x. Should there have been an x? Yes, shouldn't there? There should be an x right there. Integrating 2 should come into 2x. So this would indeed be minus 4. Glad I caught that. Now let's just kind of put things together. I'm going to make sixth out of this first stuff, so that's going to give me negative 2 6 plus or minus 3 6 plus 12 sixth. Take away 16 sixth. Oh, those sixes are not writing well. There we go. And minus 2 minus 4 is negative 6, but the outside negative makes this plus 6. Okay, I'd have negative 5 plus 12 is 7 sixths minus 16 sixths plus 36 sixths. This would create 26 plus a 7 sixths. Remember, this was 20, not whatever that looked like. Final answer, 27 over 6. All right. And finally, the last example is find the area of one regions bounded by sine and cosine curve. All right, let's identify which is, I'm going to call my upper function sine x because that's what it is, right? So this is f of x. And then I'm going to call my lower function g of x. Ooh, sorry, I wanted that a different color. So that is the cosine curve. And now the region that we're interested in, it said pick one of the regions between them. So I'm going to pick that one that's very clearly defined here. And let's find out how much space is between sine and cosine. What is the intervals of intersection, or the points of intersection? Right there and right there. Well, basically I got to find out when is sine equal to cosine. And sine is equal to cosine. Think of your unit circle. It happens on the pi over 4s, doesn't it? And here we'd have positive, positive. Down here we'd have negative, negative. So it looks like we're at pi over 4 as well as 5 pi over 4, correct? So x equals pi over 4 and 5 pi over 4. So that'll be our interval that we are looking for the area between. All right, now let's set up the interval, the integral. So area between the curve would equal an integral from pi over 4 up to, or over 2 if you want to think of it that way, 5 pi over 4. My top function is f of x, which is sine. Bottom function is cosine. Multiply by the width dx. So we have a rectangle line. In here, well, actually many, right? In infinite number of rectangles because they have infinitesimally small widths. And then it's just a matter of integrating it. And I went ahead and did this one. I guess I did do it by hand, but I'm just going to tell you. It turned out to be 2 square root 2, which was approximately 2.828. And remember, if you do it in the calculator, you must give 3 decimal places for your answer. So you've got to be accurate out to that 1,000th position. All right, your homework for the day is to look at Delta Math. Delta Math day 1, probably around 7-8 questions, okay? One part is without calculator, and I encourage you to do it without calculator. And the second part then is with calculator. Good day.